introduce something called parallel errors, right? And of course, you want to avoid that, so you go to eye level and you read it all. Right here, right? Here we have to make sure that we have things at the right level and we set them up and make sure we get the right reading. It's a popular lab. What is showing you here is when you clamp it down, you want to make sure that everything is set at the right length and angle. So you don't just clamp down the ruler and say, right, the ruler straight. You have to prove or guarantee that it's straight. So by using this set square, you make sure that it's straight. Okay? You can't try to reduce errors as much as possible. Right? So avoiding parallax errors. These occur when the experimenter is not viewing the readings at eye level. Not doing this can cause inaccurate data to be reported. When possible, equipment should always be placed on a level surface. Sometimes perpendicular aids must be constructed from set squares in order to read the instruments accurately, right? So that's a little example there. Next, sometimes you might make an error, like in the first number one. Sometimes the apparatus have errors, right? Make a note of this in your book. I'll just give you some of the important things. A random error occurs when the experimenter makes a mistake. That's a random error, right? And then a systematic error. Yes, systematic error occurs when the apparatus or the environment is faulty. A systematic error occurs when the apparatus or the environment is faulty. All right, so let's go back to zero errors. So, ready? Before using an instrument, it is important that it is calibrated to reach zero. At the start of the experiment, scales and stopwatches have an option to reset to zero, while gauges and ammeters must be checked beforehand. So sometimes you might go to apparatus, right? Right? Sometimes you might go to apparatus and you might observe this. Let's see, it's a little it's a ammeter, right? Or you're going on a scale. And instead of the arrow starting at 0, the arrow starts at 2. Right? That's a big problem, right? If the arrow starts at 2, any reading you observe will be off by how much? 2. So if you can't get it back to 0, what you will do? Benaya, what you'll do? What you'll do? Right? What you'll do? Subtract 2 from all of them. So you have to look out for that, right? Nothing wrong with the apparatus, it's just it's not zeroed. Right? If that happens, all you have to do is take a reading and minus off 2. You okay with that? Next, one that you may have experienced before, human response time. When taking readings from a stopwatch, for example, the actual time for an experiment to start and stop, the stopwatch causes a delay and accounts for a slight error. So for example, if you have to find the time it takes over a short distance for an object to fall, your human error might occur because your response time mightn't be as accurate. Okay? So that's an error that we have to avoid. Any idea how we can fix that? We have this short distance here, and I want to find the time it takes for an object to fall. What you can do? Use a machine, but it's in the lab. What you can do, yeah? Okay, you can double the distance and then find the average. Or, right, what you can do is do it like 10 times. Right? Find the time it takes for it to fall 10 times and then find the average. Okay? So sometimes what we do is repeat and find average. Right? For those who did a lab already, you may have done a pendulum lab already. No? Right? So yes, but that's one thing that you can do. Repeat the average, repeat the process and find the average. Next, two important words, accuracy and precision. Right? They are not the same thing, right? Accuracy refers to how correct the data is. So accuracy is, if the correct reading is 2 and you get 2, it means they're accurate. That's okay. If you get 1.3, it means it's not accurate. All right. Precision refers to how consistent the data is being reproduced. So if you get a reading the first time, 2.1, the next reading, 2.11, then 2.09, then 2.1. It means that all your values are very close together. So it means that you are precise. Are you okay with that? Yeah, so precision has to do with how close the values are, or how close you get the back the results. Accuracy is how close you are to the correct answer. So what you're saying? Which of these examples here is accurate and which is precise? Think about it first. Then I'll pick on somebody. Caleb. 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 Oh, Caleb 1-9. I'll try Adrian now.
One on your left is accurate, the one on your right is precise.
Very good. Right? This one here is accurate because all the values are in bullseye. The next one underneath is precise. Right? Precise, but not accurate. But okay with that? It's precise, but not accurate. So be careful in physics when you're using those words. Everybody okay with that? Actually, you know what? In case you'll never read this again, never open this handout, just write down in your own words what is accurate and what's precise. Just in case you never read it again. And remember, on the LMS, I'll be able to tell when you log in, when you use it, how long you use it for. Okay? So if you don't want to again log in and spend 5 minutes. All right? That's fine. Forget it. You got it? Yeah, go to the box. Gotta go to the box. Right, that's well done. Salamat. Yes. All right, nice. Next, we have to remember the prefixes. You may have done them in Form 1 or 2 or something. But whenever you see these symbols, capital M, capital K, lowercase k, C, M, and this micro symbol, you have to know what they represent, right? Because in physics, you don't want to keep writing 10 to the plus 6 or 10 to the minus 6. You don't want to do that. So what they do is instead they write micro. Okay? So you have to learn all the prefixes and what they mean. Everybody okay with that? Right? So as an example, write this down. Find the area given that find the area given that for a rectangle, for a rectangle, its length. Write it so you know what I'm talking about. Its length is 20 kilometers. Its length is 20 kilometers, and its width is 400 micrometers. Its width is 400 micrometers. Try now, find the area. I'm gonna say use it prefix first, and then work it out. Vegan, what are you working on for now? Huh? And yeah, so leave it like that. All right. All right, let's see what you got now. Oh wait, let me just mark this roll before I forget. Adrian, you here? Caleb online. With I on a phone there. Mariah, Chriselle, Solomon, Eden. Eden, right? Robert. Huh? One time. Why can't you still? Presley. Cairo online. Eden, Emily. Maharaj. Well, it's funny. Sarah, Priya, Hussein, and Shreya Rana. What is Hussein? Shreya, Hussein, you got it. No, that was Shreya Rana. Okay. I mean, I'm Shreya Hussein. Colleen, Alan, Israel, Amelia, Anjali, yeah, Guru, what's the first name? Tanya, Pichu, fine. Kerry, Shana, Clifford, Carissa, Sasha, Clifford, I'll see Clifford online. Teresa, Ariel, Jaden, Johanna. All right, so let's see what you got. So basically, all you have to do is just multiply, right? But I'll squeeze anything somewhere right there, right? So we know that area is equal to length by width, right? The length will be 20 by 10 to the 3, and the width will be 400 by 10 to the minus 6, right? When I go to a calculator, right, I want you to learn to use the exponent function. So put 20 and look for 10 to the power x. Or those with a sharp, look for exp. So put 20 by 10 to the power of 3 multiplied by 400 by 10 to the power of minus 6. I got 8. 8 as the answer, 8 meters squared. Right? 8 meters squared. Did I get enough? You say 13? But you multiply it by, right now you have to multiply that by 20 by 3 to find the area by 10. Everybody can do it? Right? So you're looking for, if you have a sharp EXE, if you have a Casio, you're looking for by 10 to, right? You'll see multiply by 10 to some power. That's okay? All right, nice. So again, always make sure everything in the same units. Make sure you can convert the prefix. All right? Yeah? Tamara.
Wait, what was the answer about?
8. How much you got?
80.
Oh, go. I put 10 by 10, right? So I put in 20, 10 to the 3. Multiply by 410 feet.
Oh. Okay, got it.
Ready? Let's continue. We gotta learn that right earlier. Test on that next week, right? Right? We have to be able to do some conversions and so on, right? So here's an example of, you see, kilometers per hour mightn't be too useful. So we need to be able to convert from kilometers per hour to meters per second. Oh, I do. We got to point out something here, right? We need to understand significant figures and things. So watch this here. So standard form is a means of expressing large numbers in simple ways using integral powers and using three significant figures. Now that a decimal point goes after the first significant figure. So for example, if I give you something like this, if I give you something like 54880, you don't want to keep writing those values in physics. So what you do is write the value to three significant figures. What will that be? 54199, right? 549. And then put it to the exponent. So you may or may not remember this, but if you have 54880, you have to move it to decimal place from here to the left. When you move to the left is positive. When you move to the right is negative. So 1, 2, 3, 4, right? So that's 5.49 by 10 to the 4. Everybody okay with that? Sometimes you can replace 10 to the 4 with a prefix. Sometimes, right? So you have different options. There aren't any prefix with 10 to the 4, but look at the one underneath. 0.00648, three significant figures, 6.48, and move the decimal place 1, 2, 3. So you end up with 6.48 by 10 to the minus 3. But I don't want to write 10 to the minus 3. What do I write? How much joules? 10 to the minus 3 is which letter? I'll now do that. Milli. M. Homework, learn that table. I'll make a note so that you have test on that. Right, learn the prefixes so when you see them, you know what they are, right? Learning prefixes. Okay, so what you learn there? Whenever you get an answer in physics, firstly, right? Try to do it in try to give the answer in standard form. Okay? And make sure you can convert in prefixes, right? Online, Carissa, you're okay with that? Yeah? Okay. For some of your message next. Okay. All right, nice. So scientific, oh sorry. Before we do that, we have to be able to convert kilometers per hour to meters per second. So convert 108 kilometers per hour to meters per second. How are we doing that? Right? How are we doing that? First, you have to figure out what does 108 kilometers per hour mean? What does that mean? 108 kilometers in how much? In an hour, right? That's okay? So it means 108 kilometers in 1 hour. Then what do they think? What do they have now? Data. So that's some nothing. Oh, bring in here. Right, yeah. So what does 108 kilometers per hour mean? It means that in 1 hour, you're traveling how much? 108 kilometers. right? So how do we convert that to meters per second? Number one, can we convert the kilometers to meters? Multiply by 1,000, right? 10 to the 3. So now you have 108,000 meters. Can we convert hours to seconds? How you do that? Times 60 times 60. So times how much? 3,600. Are you okay with that? So 1 hour has 3,600 seconds. What's that? Oh, she doesn't know. Right. So yes, so that will be 3,600 seconds. But I want meters in 1 second. So divide by 3,600. That's what they did here. They multiply by 1,000 and divide by 3,600. Yeah. So your final answer is 30. Okay. Try example. Try a small example. Convert 80 kilometers per hour to meters per second. Convert 80 kilometers per hour to meters per second. And when you finish, convert 100 meters per second to kilometers per hour. 100 kilometers, 100 meters per second. Convert meters, convert kilometers per hour to meters per second, and then do the reverse. All right, so I come up with.
Yeah, I think so.
100 meters per second to kilometers per hour. Right. What's it? Right, let's go, right? First one is what? 80 kilometers per hour to meters per second. So as we saw in the last one, all we have to do is take 80, multiply it by 1,000, and then divide it by 3,600. Okay? How much is that? 22.2 meters per second. 22.2. Everybody okay with that? Now we have to do the reverse. Right? We have to do the reverse now. What's the reverse? The reverse now is taking meters per second and going to kilometers per hour. Right? I'm going to do this now. Let's copy this one now. Right, let's check it out. 100 meters in 1 second. Okay, so how many kilometers is that? Divide by 1,000, right? Now we divide them by 1,000. So if I divide by 1,000, I will get 0.01 kilometers in 1 second. How do I find now for 1 hour? Multiply by what? Multiply by 3,600. Right? So we'll get 1, 2, what we get? Oh, sorry.
Yeah.
1, 2. I just say what man. Right? And then you multiply it, right? So you'll get 360. Yeah? 360 kilometers in an hour. So it's divide by the other way around. Divide by 1,000 and multiply by 3,600. How you do?
Then something, I guess I did.
Huh?
Something is going to get 6.
That was something I don't know.
Okay, so from 100 oh, 100 multiplied by 3,600.
Right?
Then I get 260 shorter,
And then inside.
and then it's 5. Yeah.
Same thing, that's a different order.
Okay.
Same thing as a different order. Are you okay with that? Well, looking so weird. Anyway, so 100 meters per second is 360 kilometers per hour. That's okay? So we did the reverse. We divide by 1,000 and then we multiply by 3,600. That's okay? I have a shorter way, but I don't want to show you. Or should I? Right? Okay, well, technically, take 100 and multiply by 3.6. what you can do is you can combine these two into one. Yeah, combine the divide by 1,000 and multiply into one. Right? But you might remember that for exam. In exam, you might remember, okay, convert meters to kilometers and then seconds. So you might remember that. But if you can remember the shortcut as well, just divide by 3.6. All right, let's go again. All right. Next, forget this lab thing. You all do that in school. Right? We did gradients, we did graphs, how to plot. Remember, I like the graph to be nice and big and so on, right? Next, we have two definitions to understand. Scalar and vector. What's the difference between a scalar quantity and a vector quantity? Scalar has magnitude only, no direction. Vector has what? Magnitude and direction. So if I said a scalar quantity has magnitude alone, no direction. So for example, if I said find the length, I'm not going to tell you how to find the length. Right? I'm not going to tell you where to start, where to finish, you just find the length. Right? So here we have some examples: distance, speed, area, volume, density. Okay. Vector quantity has both magnitude and direction. So for example, if I said apply a force, I have to tell you what direction to apply it in. So what does that mean? It means that force is a vector quantity. Okay. So if you look here, a vector quantity is displacement, velocity, force, acceleration, vector. Are you okay with that? There are two quantities I want you to learn the difference between them. I have mass and weight. Mass and weight, distance and displacement. So I'm going to show you two examples, and I want you to tell me if you could figure out the distance, the difference between both of them, right? Mass and weight, distance and displacement. So here I have two diagrams. One diagram labeled as mass and weight, and distance and displacement. See if you can figure out, draw them. See if you can figure out what is different between them. Right? So what's the difference? Let's look at mass and weight. What's the difference between mass and weight? In fact, which do you think is a vector and which is a scalar? Weight is mass is scalar, mass in here, no arrows inside it. Weight is what? Vector because it has an arrow showing you, right? Displacement. Arrow, in the arrow. Distance, scalar. That's okay? So what's the difference in terms of definition? What's the difference in terms of definition? Right? Mass is the amount of substance. Weight is the effect of gravity on the mass. Okay? So make a note of that. Mass is the amount of substance or the amount of matter. Mass is the amount of matter in a substance. Mass is the amount of matter in a substance. Mass is the amount of matter in a substance, while weight is the effect of gravity. While weight is the effect of gravity. While weight is the effect of gravity on substance, right? SI units. Right? SI units. Weight is in newtons. Mass is in kilograms. I should make a note there, you'll be using that formula a lot, right? Weight is mass by gravity. Right, so I want you to remember this formula, put it in coloring. You'll be using it a lot. Question. If you go on the moon, right? If you go on the moon to live, right? Would your mass change?
No.
Your mass wouldn't change, but yeah, the weight will change, right? Because gravity will change. Right? This is nice. Make a note of that. Note that your mass is constant. Your mass is constant. Your mass is constant, but your weight is affected by gravity. Here, let's take a small note. Right? So you need to understand when they ask for which one, right? Distance. Distance is the total length traveled. Distance is the total length traveled. What do you think displacement is? Distance, okay. So displacement is this straight line distance, displacement, right? Straight line distance from start to finish. Straight line, right? Notice straight line distance from start to finish is a displacement. Right? Let me just give you one popular example I like to give. Normally I'll give you what? But change it up to the I remember area. Sorry. The triangle of the rectangle. Right, so I just giving you a little small thing here. Small little one. Actually, let me change the number. I'm gonna give you some nice numbers. So I want you to find for me a little table away to fill up, right? You have distance in meters and you have displacement. So in each of the cases, I want you to try to figure out what is distance and displacement. Each of the cases. So here we do, right? Ready? Are they all? Yeah. Right, Sanjaya, help me do the first one now. 4. Both will be 4. That makes sense? Both will be 4 because we start here and finish here. Right? Next one. Let us go with. Why and pick one in a while. Ross. Ross help out here now. O to A. Okay, no. But you gotta do a little something here. Huh? Pick. I'm gonna pick Benaya. Benaya. This one is for you.
Okay.
O to A to B. How much is that?
7.
Right? 4 plus 3, which is 7. But you start here and you finish here. So you have to use Pythagoras theorem. Okay? Here is 90. That's okay? So you have to use Pythagoras theorem here. Because I want start to finish. When you use Pythagoras theorem, you got 5. That's okay? Yeah? Russ, your turn now. O to A to B to C. Start here. Finish right here. What's the total distance traveled? How much is here, by the way? How much? If here is 4, how much is here? It's a rectangle. Here is 4, right? If here is 3, how much is here? Right. Tell me, here to here to here. 11. What will be the displacement though? Start here and you finish here. How long is that? 3. Yeah, 3. Next, let me go with let pick somebody online now. We all think not working in. Obviously, like pick somebody who most likely fall asleep. Kyra? Kyra? Kyra, what do you think is the answer here? Kira. Kira? Correct, my last name? Kira. Mongo? Kira. Hey, same spelling. Kira / Kyra. What do you think is the answer here for total distance traveled? Okay, she's not here. Let's pick somebody else online. Let us pick Caleb. Caleb or Jenna Marie, whoever answers first. Caleb or Jenna Marie, what do you think is the total distance traveled here? Oh Lord, nobody behind that, no? Oh, Jenna answered. Jenna said 14. 4 and 4, 8 and 6, 14. Nice. And what's the total displacement? You start here and you finish here. Anybody online could answer? You know what? You can look up, you don't know. Sasha, what you got? 0? 0 could work. 0 could work online. I didn't have in person. I wasn't sitting on it. That's valuable as well. I suppose we'll pick up some fast man and be doing the work, but it doesn't break down. But when they join the element, how to see how it is. Huh? Yes, put that. What's the question? What you say? Your message? Who? Versus you? All right, nice. Well, okay with that? So that is scalar and vector quantity. The next thing we have to do is forces, but you'll have protractor and compass. Protractor. Ruler. And on the protractor. Protractor is the half a circle, you know. You all know have that?
Yeah, I have mine. And it's
But everybody have to have one. All right. We will get to the ruler and try to average 90, right? So head up resolving. In fact, head up result. Finding the resultant force. Finding the resultant force. Right? It's something I would have done in Form 1 or 2 or something, right? Form 3. Finding the resultant force. I can't do all the different types, but I'll do the initial types, right? So let's start easy. How do we find the resultant force? You all will recognize here that we learned a little while ago that forces are what type of quantities? Forces are what type of quantities? Vector. Forces are vector, right? So one direction positive, next will be, one will be nice. So it don't matter which one you choose, just be consistent, right? So if I ask you here to find the resultant, all you have to do is add it up, right? So here you have what? Positive 5, here you have negative 4. So you're going to add positive 5 to negative 4 and you'll get 1. What does this 1 tell you? This 1 tells you that it's moving to the right, 1 Newton. Is that okay with that? This one, same principle. Resultant force, that'll be positive 6 plus minus 2. So that'll be 4 newtons upwards. Right? 4 newtons upwards. You okay with that? So for these, you can just use a ruler and draw them. The next one though, continue the parallelogram law. All right, everybody watch here. Oh, you're drawing cells? Okay. Someone already? Do what? Yeah, to work it out, yeah, but. Ready? So watch this here. We don't have much time. I'm gonna show you this last thing here. So let's say we set up a scale diagram. Yes, we could use a formula, but in physics, initially, we need to understand how to use parallelogram law, which is a scale diagram. Scale meaning for every centimeter, it must equal to some newtons. So let's say 1 centimeter is 1 newton. The angle between these two is what? 90 degrees, right? So we're going to draw a line 6 centimeters long, average 90, right? And then draw a line 8 centimeters long. Watch this here. Here's the hard part. The hard part is we have to complete parallelogram. So I have to draw a line parallel to this, 6 centimeters long, a line parallel to this, 8 centimeters long. So in our example, we should have a little rectangle. Okay? Once you have that now, think about it. If you have two forces, one pulling up and one pulling to the right, where would this object move? It'll move along that diagonal, right? So it means that our resultant should lie right here. Okay? So use your scale and then tell me what is the length and then convert it to Newton. Okay? And you're done. 6 centimeters, 98, and then do the scale. Right? We can't do the others because we do have protractors, right? We'll walk with a protractor at the half a circle, right? Walk with that next. Please spend a few minutes and go over the things that we did this week because we do have a lot of questions next week. All right? Am I finished? What you got? Right? If you do it perfectly to scale, you should get a value. No calculator. You should need a calculator. You just, when you do it 6 and 8, all you have to do, because we're not using Pythagoras theorem, all you have to do is take your ruler and measure the length here. That's all. Everything is pure measurement. Right? So it must be exact, yeah? 6, 8, and then measure the middle. What you got? 10. Right? The answer is 10 if you do it properly. Exactly 10. Right? And that's parallelogram law. Do it again. You can get here. So you have to figure out angles and forces that's the number. So it will be same.
I think I should have that.
But it's good because it will come out of that. But so if
Oh, thank you.
that was here yesterday, that is said, the recommendation, but that's not 65, but question. So hard. 10. Go ahead.
Oh, buddy. Yeah.
All right. That's it there, earlier. Right? So remember next week we do a lot of questions, past papers, and then we focus on that's all you all do it next week.